Welcome to Module 5 of our Electrical Grid Testing and Commissioning Training Series. This session focuses on grounding transformers, a crucial component to ensure safety and stability in our electrical systems. As we go through the training, we'll cover key concepts and practical approaches to effectively test and commission grounding transformers. Let's dive in and build a solid foundation for your expertise in electrical grid management. On this slide, we present the reference framework used for testing and commissioning electrical grids. These references form the foundation for our commissioning manual and test scripts. Key organizations include IEC, which stands for the International Electrotechnical Commission, and IEEE, the Institute of Electrical and Electronics Engineers. We also rely on ASTM, the American Society for Testing and Materials, NEMA, or the National Electrical Manufacturers Association, and ANSI, the American National Standards Institute. Additionally, CIGR represents the International Council on Large Electric Systems. ICA is the Insulated Cable Engineers Association, and KEMA serves as a verification body for electrical engineering standards. It's important to apply the most stringent approved requirement whenever there is a difference between project specifications, manufacturer instructions, and standards. Always record the reference used on the test sheet to ensure that future reviewers can understand why a particular result was accepted. This approach guarantees consistency and traceability throughout the commissioning process. Here we have the schematic reference for the 5 kV DC insulation resistance testing of the grounding transformer winding and neutral path. This test is crucial to ensure the integrity of the winding insulation before the transformer is commissioned. By verifying proper insulation resistance, we can prevent potential faults and improve the reliability of the electrical grid. This procedure is detailed in Commissioning Manual number 5-1, which guides us through the correct testing methods and safety precautions. Let's go through the grounding transformer winding insulation resistance test script step by step. First, we need to confirm the transformer tag, rating, winding terminals, and the approved test boundary to ensure we're testing the correct equipment. Before testing, it's essential to review all safety permits, lockout-tagout status, discharge status, grounding plans, and confirm the area is properly barricaded. Cleanliness is critical, so we clean all bushings and terminal surfaces to remove dust, moisture, or any conductive contaminants. Next, we connect the insulation resistance tester according to the approved schematic, focusing on the winding to ground boundary. We then apply a 5 kV DC voltage for both 1 and 10 minutes, watching carefully for stable readings and any abnormal discharges. We must record the readings at both intervals, along with environmental conditions and the equipment's serial number. Using these values, we calculate the polarization index by dividing the 10-minute reading by the 1-minute reading. Finally, discharge the winding safely, restore all links and grounds, and document the as-left condition. The insulation resistance must meet the approved limit, generally above 10 megohms, and the polarization index should be at least 1.25 where required. There should be no flashover, tracking, or abnormal discharge during the test. All results, including the IR readings, PI calculations, connection photos, environmental conditions, calibration certificates, witness signatures, and restoration records, form the evidence package. A hold point is included where a witness confirms the accepted readings and safe conditions before any further steps are taken. This thorough approach ensures the winding insulation is intact and the transformer is ready for energization. Here we have the schematic for the grounding transformer's core and frame insulation, which is crucial for ensuring the safety and reliability of the electrical grid. This diagram serves as a reference for conducting insulation checks at 1 kV DC between core-to-earth, frame-to-earth, and core-to-frame. These tests help identify any insulation weaknesses that could lead to faults or failures. Following this schematic carefully during testing and commissioning is essential for maintaining proper operation and preventing electrical hazards. Here we focus on the grounding transformer's core and frame insulation test procedure, which is critical for ensuring safety and reliability during commissioning. First, we confirm the transformer is fully isolated and identify the core, frame, and earth links based on the approved drawings. Then, under strict isolation and grounding instructions, these links are carefully removed to prevent any electrical hazards. Next, we clean all connection points to avoid any parallel bonds that could interfere with accurate measurements. We conduct insulation resistance tests at 1 kV DC between core to earth, frame to earth, and core to frame, holding each test for the required duration while monitoring for stable readings or any discharge. All relevant data, including test voltage, duration, insulation values, ambient conditions, and terminal status, are meticulously recorded. After each measurement, the system is safely discharged, and all links are restored to their original configuration. Verification ensures bonding continuity is intact before final acceptance. The insulation must meet the manufacturer's and project's specific limits, with no unexpected low-resistance paths. Documentation includes the insulation resistance report, photographic evidence before and after link removal, calibration certificates, and witness signatures. At the hold point, an authorized witness confirms link removal, restoration, and accepts the insulation test results, ensuring compliance and safety before proceeding. Here we have the schematic for measuring the winding resistance of the grounding transformer, specifically for the RN, YN, and BN windings. This is crucial because accurate winding resistance measurements help us verify the transformer's integrity and detect any potential issues before the system is energized. You'll also notice that temperature correction is included in this schematic. This is important since resistance values can vary with temperature, and adjusting for this ensures our readings are reliable and consistent. Overall, this procedure is a key part of the testing and commissioning process outlined in Commissioning Manual Number 5-3, helping us guarantee safe and efficient operation of the electrical grid. On this slide, we focus on the grounding transformer winding resistance test, which is essential for ensuring reliable transformer operation during commissioning. The key here is to confirm winding continuity, check phase balance, and apply temperature correction to resistance values for accurate assessment. We use calibrated low-resistance ohm meters with Kelvin leads, along with thermometers and cleaning kits, to perform the test step by step. It starts by confirming the winding terminals and transformer details, then isolating and cleaning terminals to avoid measurement errors. Next, we connect the Kelvin leads according to the schematic, inject DC current, and wait for stable resistance readings on each phase. After measuring and recording resistance, temperature, and instrument details, we correct the resistance to a standard 75 degrees Celsius. The critical step is to compare these corrected values against factory baselines to identify any abnormal deviations or imbalances. Any unstable contact, open circuit, or unusual reading must be addressed before proceeding. The test concludes by restoring terminal covers and completing the test documentation. Acceptance requires that the temperature-corrected winding resistance is phase-balanced within project limits, backed by a comprehensive report including raw data, photos, calibration certificates, and witness signatures. A hold point ensures that a witness confirms phase balance and temperature correction before moving on to the next stage. Here we have the grounding transformer temperature sensor calibration schematic, which is crucial for ensuring accurate temperature readings during operation. This schematic provides a detailed reference for the oil temperature indicator and the method of winding temperature simulation through secondary injection. By following this approach carefully, we can verify that the temperature sensors are calibrated correctly, preventing potential overheating issues. This procedure is an essential part of the testing and commissioning process for the electrical grid, as documented in Commissioning Manual Number 5-4. Today, we're focusing on the grounding transformer temperature sensor calibration process. This procedure is crucial for ensuring accurate oil and winding temperature indication, alarms, and overall supervision readiness. We start by confirming the sensor tags, alarm and trip set points, wiring terminals, and the control panel interface to make sure everything is correctly identified. Next, we set up the heated oil bath and secondary current injection safely, which serve as our reference points for calibration. The oil temperature sensor is then immersed at staged reference temperatures, and we carefully record the indicator readings and deviations at each point. For the winding temperature, we inject a heating current as specified, recording the temperature before and after to simulate a temperature rise. Verification of alarm and trip contacts, as well as local and remote indications, follows to ensure proper functionality. Finally, we restore the sensor circuits, capillary routing, panel status, and confirm normal indications. The acceptance criteria specify that the oil temperature indication must be within plus or minus 3 degrees Celsius or the manufacturer's limits, while the winding temperature simulation and alarm operations must match the transformer manual and approved settings. Documentation includes a calibration table, reference thermometer certificate, injection records, alarm screenshots, and a witness sign-off, which holds a critical hold point where the witness confirms calibration accuracy, alarm and trip path integrity, and normal system restoration. Here we have a schematic diagram related to the grounding transformer, specifically focusing on tan delta testing for 10 kV systems. This illustration is vital for understanding how to perform power factor or tan delta tests on the winding paths of the grounding transformer. These tests help us identify insulation integrity and detect early signs of deterioration. Accurate tan delta measurements ensure the reliability and safety of the electrical grid during commissioning and ongoing maintenance. Keep this schematic handy as a key reference in the commissioning manual number 5-5. Today, I'm going to walk you through the grounding transformer tan delta test, which is crucial for evaluating insulation dielectric condition. This test measures charging current, watt loss, power factor, and capacitance to assess the transformer's health. First, make sure the transformer is fully isolated, discharged, and the bushings are cleaned before connecting the test set. Identify the RN, YN, and BN terminals, along with the neutral path and approved test boundary. Then, connect the tan delta test set, including the guard and ground leads, exactly as per the schematic. Next, apply a 10 kV test voltage to each phase, starting with the RN path, and carefully monitor the charging current and watt loss. Repeat this for the YN and BN phases using the same connection pattern. During testing, record the power factor or tan delta, capacitance, test voltage, and environmental conditions. Once you have the data, compare each phase's results to the approved limits and baseline trends. The key acceptance criterion here is that the power factor or tan delta must be below 0.5%. Any reading above this or any phase anomaly means an immediate investigation and retest are necessary. After completing the test, discharge the transformer, remove all temporary connections, and restore the grounding and terminal conditions. Finally, prepare the result package, which includes the tan delta report, raw test files, connection photos, calibration certificates, and witness sign-off. Before you release the transformer, a hold point requires a witness to confirm the dielectric results are acceptable and that there are no unexplained phase deviations. This step ensures the safety and reliability of the electrical grid. Here we have a schematic related to the grounding transformer, specifically focusing on the oil dielectric breakdown test. This test is crucial because it helps us assess the insulating properties of the transformer oil, ensuring the transformer operates safely and reliably. Regular sampling and dielectric breakdown voltage testing allow us to detect any deterioration or contamination in the oil before it leads to serious issues. This schematic serves as a detailed reference for conducting these tests during the commissioning of the electrical grid, following the guidelines from commissioning manual number 5-6. Understanding this process is key to maintaining the overall health of the grid infrastructure. This slide outlines the comprehensive script for testing the dielectric breakdown of grounding transformer oil. The primary goal here is to ensure the insulating oil's dielectric strength meets the required standards before the transformer is energized or accepted for service. We begin by verifying the sample point, oil source, transformer tag, and the approved sample identification to maintain accuracy. The testing equipment must be properly grounded and placed on a dry, stable surface to ensure safety. Next, the test cup is cleaned and dried thoroughly, filled to the specified level, and we carefully remove any air bubbles to avoid interference in the test results. After filling, the sample stands for 3 to 5 minutes to stabilize. Then we apply a voltage ramp until dielectric breakdown occurs, recording the exact breakdown voltage. This process is repeated as needed according to the approved procedure, and all values are documented for thorough evaluation. The final step involves calculating and comparing the results against project and manufacturer acceptance criteria. The minimum acceptable breakdown voltage is typically above 50 kilovolts, as shown on the poster. Any contaminated, inconsistent, or poorly labeled samples are deemed unacceptable. We then properly close and label the sample point and restore the site. The result package includes the oil dielectric breakdown voltage report, sample label and chain of custody, tester calibration certificates, photos, and witness signatures to ensure full traceability. The hold point requires a witness to confirm the sample source, result traceability, and that the dielectric strength meets acceptance criteria before moving forward. This meticulous process guarantees the reliability and safety of the grounding transformer insulation system. Here we have the schematic for the grounding transformer impedance measurement, an essential part of testing and commissioning the electrical grid. This diagram shows the setup for a 380-volt three-phase injection, where we measure both phase voltage and current. By analyzing these measurements, we can accurately calculate the transformer's impedance, which is crucial for ensuring proper grounding and overall system safety. This process is detailed in Commissioning Manual number 5 to 7, providing step-by-step guidance to carry out the test effectively. On this slide, we focus on the grounding transformer impedance measurement test script, an essential part of testing and commissioning the electrical grid. The goal here is to verify the phase impedance by injecting a controlled three-phase voltage and measuring the corresponding phase current. We rely on several key instruments, including calibrated ammeters and voltmeters, a protected 380-volt three-phase supply, temporary leads, and necessary personal protective equipment and barriers to ensure safety and accuracy. The step-by-step procedure begins with confirming the winding terminals and the isolation status, followed by verifying the protection of the temporary supply, the calibration of meters, and communication with the test authority. Then we connect the supply and measuring instruments as per the schematic, energize under controlled conditions, and observe for any abnormal noise, heating, or imbalance. We record the input voltage and phase currents, calculate the phase impedance using the formula Z equals the applied voltage divided by the square root of 3 times the measured current, and compare these values with the approved design or factory data to check for balance. After the test, we de-energize, discharge, remove temporary leads, and restore all terminals. The crucial acceptance criteria demand that the calculated impedance and phase balance fall within the manufacturer's tolerance, with no abnormal signs such as imbalance or unstable current. Finally, all results are documented thoroughly in an evidence package including calculation sheets, measurement records, connection photos, calibration certificates, and a witness signature. The entire process is paused at a hold point where a witness confirms supply isolation, accepted calculations, and proper restoration before moving forward. This thorough testing ensures the grounding transformer performs safely and reliably within the electrical grid. Here we have the schematic for the grounding transformer supervision functional check. This diagram is essential for understanding how to properly test and commission the electrical grid components related to the grounding transformer. It includes key references for the MK panel, protection relays, alarms, trips, as well as the HMI workstation and gateway checks. Following this schematic ensures that all supervision functions are verified accurately, which is critical for maintaining grid safety and reliability. The details are outlined in Commissioning Manual number 5 to 8 for further guidance. This slide covers the grounding transformer supervision functional check script, which ensures proper testing and commissioning of the electrical grid. The key focus here is the functional validation of protection, alarm, and trip supervision from the field device all the way to the MK panel and remote HMI. We start by confirming the transformer is grounded and the control supply status, referencing the approved MK scheme drawing. Then we identify critical protective devices like the Buchholz relay, oil level, pressure relief, and temperature sensors. Next, wiring continuity and scheme markings at the MK panel are thoroughly checked. We simulate each alarm and trip contact in line with approved methods and device limits to verify proper operation. Local enunciation, HMI or gateway indications, and event records are closely monitored to ensure accurate reporting. For trip functions, a command is proved to the related circuit breaker under controlled test conditions. All results are carefully recorded, including pass or fail status, circuit modifications, and corrective actions. Finally, alarms are reset, normal status is restored, and we confirm no unresolved abnormal indications remain. The acceptance criteria are strict. All alarms and trips must match the scheme, settings, HMI labels, and breaker response. Any missing, misnamed, or non-functional supervision points are considered open defects. The result package includes functional checklists, screenshots, event logs, a trip matrix, correction logs, and witness sign-off. A hold point ensures that a witness confirms the trip and alarm paths and verifies normal restoration before the equipment is released. This systematic approach guarantees a reliable and safe grounding transformer supervision system. Here we have the schematic for testing the grounding transformer's cooling fan. This diagram is essential for verifying several key parameters, including the insulation resistance of the fan motor, the starting and running currents, as well as checking for single phasing and ensuring the fan is rotating correctly. By carefully following this schematic, we can guarantee that the cooling system operates reliably during commissioning. This is all detailed in Commissioning Manual number 5 to 9, which provides comprehensive guidance throughout the testing process. Here we have the complete test script for grounding transformer cooling fans, covering all essential steps for ensuring proper operation. First, we verify fan group tags, motor ratings, supply, and work permits. Then, after grounding and isolating fan circuits, we measure insulation resistance for each motor via the terminal block. We proceed by starting each fan to record the three-phase starting current, followed by measuring running currents once stabilized. These currents are summed by phase to assess the group's electrical performance. Next, we carry out a single-phase loss protection check and record the response time. Finally, we confirm the rotation direction before restoring all phases and returning fans to automatic mode. Throughout, acceptance criteria require insulation resistance, current balance, rotation, and protection responses to meet manufacturer specifications, with no phase loss or abnormal currents allowed. All results, including test sheets, readings, rotation checks, and witness signatures, form the documented evidence package. The hold point is when the witness confirms fans are back to normal automatic operation with no alarms active. This thorough process ensures the grounding transformer cooling fans operate reliably and safely.